this is the last question of chapter 2. This is exercise 2.11. The question states, explain why the second order nonlinear susceptibility of a material that possesses inversion symmetry So what does inversion symmetry mean? It means invariant under the transformation of r going to minus of r being the vector from the origin to the point in question. So this has to be, the nonlinear susceptibility of such a material has to be 0. So this is part A of the question. Part B of the question states that isotropic media such as gases, liquids, and glasses may be treated as materials with inversion symmetry on account of their lack of long range order. It is therefore the case that chi2 is equal to 0 for these materials and the dominant nonlinear effects arise from the third order non-linear susceptibility one important consequence of one important consequence of third order nonlinear effects is that the refractive index depends on the intensity the nonlinear refractive index N2 is defined according to the following expression, where N0 is the linear refractive index and I is the optical intensity. On the assumption that N2I is much less than N0, show that the following is true, that N2 is given by the following expression. So let us just read this question once again. It's a big question over here. So the first part of this question says that explain why the second order nonlinear susceptibility of a material that possesses inversion symmetry is supposed to be 0. So we need to see that chi2 for an inversion symmetric material is equal to 0. The second part says that isotropic medium having inversion symmetry will have a long range, they will not have long range order. So such materials as shown in part A would have chi2 equal to 0. So in such kind of crystals, if chi2 is equal to 0, then the nonlinear effect would have to come from the third order nonlinear susceptibility. In these situations, the refractive index turns out to be dependent on the optical intensity, and we are supposed to find out this expression for N2, which is the term multiplied, which is the refractive index multiplied to the optical intensity. So let us now try and solve this question. We need to prove certain things in this question. So the first one, so before starting this question, we need to understand what is inversion symmetry. So inversion symmetry means that the function is invariant under the transformation r going to minus r. This means that if we have a function of r, then this is equal to function of minus r. R is the position vector. From the origin to the point under consideration. Now let us see some examples of functions, and then let us see whether they are inversions, symmetric or not. So, and these examples would basically help us in solving this question. So first let us start with the velocity vector. So velocity vector is given as the rate of change of position vector. Now in such a case, if we look at the inversion symmetric version, let's say at minus r, so this is going to be the derivative of minus r with respect to t. Minus can be taken out. So clearly velocity vector is not inversion symmetric. So v of r is not inversion symmetric. Why do we say so? Because v of minus r is not equal to v of r. In fact, it is negative of v of r. Now acceleration vector is rate of change of velocity vector. So in this case, if we consider acceleration at minus r, this would be the following. Now from the above we know that v of minus r is minus v of r. Again taking minus common, minus outside, sorry. So this gives us minus a of r. Again, a of r is also not inversion symmetric. This is because we see that a of minus r is not equal to a of r. In fact, it is the negative of a of r. Now what is force? Force is mass times acceleration. So in this situation, force at r, basically, let me rewrite this. Force now mass is invariant under inversion, so mass is the same wherever it is present. Mass doesn't change under inversion operation. So from here, if we look at force at minus r, this would be mass times acceleration at negative r, and acceleration at negative r is nothing but minus x of acceleration at r. So this is minus f of r. Again, force is also not inversion symmetric. Because force at minus r is not equal to force at r. It is the negative of force at r. Now, we also know that in the case of electrostatics, we have force is equal to charge times electric field. So let me rewrite this. So force at a point R is equal to charge times the electric field at R. Now charge denoted by Q over here, charge is also inversion symmetric. Charge doesn't change under inversion operation. It is a constant and it remains the same. So in such a situation, now we know that force at R is equal to Q times electric field. So let us find force at minus R. This is Q times charge times electric field at minus R. Now we know that force at minus R is minus of force at R from this relation, because force is not inversion symmetric. So we know that this is going to be negative of force at R. So from this we get, this means that, and force at R is equal to Q times electric field at R. This is by definition. So from here we have the following. This means that electric field at minus R is negative of electric field at R. So again, electric field is also not inversion symmetric. Because electric field at minus R is not equal to electric field at R. It is the negative of the electric field at R. So we have this relation. This is an important relation. We will use this later on. Now let us come to the definitions of the polarization, the nonlinear terms in the polarization. So polarization is defined as follows. So on and so forth. This is the linear term. This is second order nonlinear term. This is third order nonlinear term, and so on and so forth. We need to focus on the second order nonlinear term. So for the second order nonlinear term, the contribution to the polarization is the following: epsilon naught chi 2 times E squared. We need to focus on this term. So if we rewrite this in terms of the position vector as a function of position vector, epsilon naught is a constant. It doesn't depend on position vector. So this is the nonlinear contribution to the polarization. Now we need to look at its value at minus R. So P2 at minus R is going to be the following. Now E squared at minus R is basically E at minus R times E at minus R. Now E at minus R we saw over here in this equation is minus of E of R. So this is minus E of R times minus E of R. So this is nothing but E squared of R. So E squared happens to be symmetric under inversion. So we get the following. Now we have polarization defined as follows also. In polarization, the basic definition of polarization is dipole moment over volume. Now dipole moment is charge times the distance between the 2 point charges. So dipole moment is basically given as the following: charge times the position vector of that given charge. We take this, if we have multiple point charges, then we will take the sum of these quantities, but in terms of dimensions, it is charge times the distance. Now in this, if we let R go to minus R, then charge times R will go to minus of charge times R. This means dipole moment goes from QR to minus QR. So since dipole moment goes to negative under inversion operation, thus we will have polarization at minus R will be equal to minus of polarization at R. This is because dipole moment changes sign under inversion. Dipole moment at minus R is equal to minus of dipole moment at R. So since polarization changes sign, polarization is also not inversion symmetric. So because of this, we will get the following. Now let us use this to solve the problem. We had over here found out the expression for P2 at minus R. So let us write it down. Once again, P2 at minus R is the following. And P2 at R is the following. Now, since we know that P2 at minus R is negative of P2 at R, from these three equations, we get the following. So we can simplify this, rearranging some terms. Now epsilon naught is a constant, it is non-zero. Electric field squared, magnitude of electric field squared will also be non-zero for a non-zero field. So this gives us the following. But we are given that the second order nonlinear susceptibility possesses inversion symmetry, but we are given in the question that the second order nonlinear susceptibility possesses inversion symmetry. So if it possesses inversion symmetry, we will have the following. So from this expression and this expression, we can conclude that chi2 is equal to 0. This is because we have one expression saying chi2 at minus r is equal to chi2 at r, and another expression saying chi2 at minus r is equal to minus of chi2 at r. So a number can be equal to its negative only when it is equal to 0. This is because from these two equations we get chi2 at r equals to minus of chi2 at r. So a number equals its negative only for the number being equal to 0. So from here we get the following, and this solves the first part of the question. So the first part of the question, which said that second order nonlinear susceptibility of materials with inversion symmetry would be 0. Let us now look at the second part of the question. So part B. In part B, we are given isotropic media possessing inversion symmetry. So inversion symmetry, meaning we just proved in part A that chi2 is going to be 0. So if chi2 is 0, then the next nonlinear term would be chi3. So nonlinear effects would come from chi3. So if chi2 is 0, then nonlinear effect comes from chi3. And we are given that the refractive index is from, it takes the following form, where this n2 is nonlinear part and n0 is linear part. So let us write down the expression for polarization. Plus 1 and so forth. Let us consider the first three terms. This is linear, this is second order nonlinear, this is third order nonlinear, since chi2 is equal to 0, we have the following. Let us write down the electric displacement vector in such a scenario. So electric displacement vector is epsilon naught E plus P. So this is epsilon naught E plus P we have from this expression. So this term right here is relative permeability in the case of nonlinear crystals. We also know that 1 plus chi1, the linear susceptibility, is relative permeability in the case of linear crystal, L denoting linear, NL over here denoting nonlinear, and this is nothing but square of the linear term of the refractive index. So from here we have now we can find out the refractive index for the case of nonlinear crystals. In the nonlinear, so refractive index is square root of the relative permeability. We take the magnetic permeability to be equal to 1 for non-magnetic materials. So refractive index is simply square root of the relative permittivity. Epsilon r is permittivity, mu r would be permeability, which is taken to be 1. So this gives us the following. Let us do some simplifications. Let us take n naught squared common. Now let us look at the formula for intensity. So intensity is proportional to the magnitude of the electric field square, and it is given by this expression out here. So from this, if we rearrange, we get electric field squared as follows, and n over here is basically for the linear term. This n out here is for non-linear. Now we can plug this value of E squared over here and get the expression for the non-linear refractive index. Now in the question we are given that n2 times I is much smaller than n0, which means n0 is much larger. It is significantly big number. So in this kind of a situation we can use binomial theorem. We can use the binomial expansion. So this term out here is going to be small in comparison to 1. So we can use from binomial expansion. This comes from binomial expansion. Let us simplify the expression. So this is n0, 2 cancels out here, plus chi 3I over n0 squared c epsilon naught. This n0 and this n0 would cancel out. So this, if we write in the following form, gives us n2 is equal to chi 3 over n0 squared c epsilon naught. So this solves even the second part of the question, wherein we had to find this expression for n2 in the case of nonlinear crystals having inversion symmetry, where the third order nonlinear effect is the dominant nonlinear effect. So this completes the questions of chapter 2 in this book by Mark Fox on quantum optics. This was the last question in this particular chapter on classical optics.